All right. Hello, everyone. My name is David Finlayson, and I'm Chief Scientist for Chesapeake Technology. And I'd like to welcome you to our second March Madness webinar. Today's webinar is going to be focused on the updates we've made over the last year in Magnetometer, the Magnetometer module. And let's get started. So, in keeping with our basketball theme, here we have the Earth and its magnetic fields coming out, which is what we're going to be talking about today. So to focus this webinar, I'm going to spend some time talking about magnetic anomalies, and then this concept called a minimum detectable target, which is an important variable that you need to know when you're planning a magnetometer survey, and then after you've actually gone out into the field and collected data. This can tell you about this equation I'm going to show you will help you estimate how much iron was down there, how big the mass is of the targets you're finding. It's really useful. Then I'm going to walk through some magnetometer processing problems and solutions that SonarWiz provides for you. And then finally, we're going to switch up and actually show you some demonstrations of SonarWiz and how it works and some of the new changes that we've made over the last year. So a little housekeeping. If you have any questions about the presentation at all, use the GoToWebinar question panel that's on the, when you're actually logged into GoToWebinar, you've got this little question section. And if you put any questions in there, we'll try to answer those throughout the presentation. If we don't get to them, we have a little bit of time at the end of the presentation. If I have some time, I'll answer them there. If we can't get to them, you can always write to support@chesapeaketech.com, and either Patrick or myself will answer those questions as they come in, especially if you're watching this on YouTube or something like that. You can go to support@chesapeaketech.com. Now, before we get into the current changes that have been made, we did a webinar about 2 years ago, actually exactly 2 years ago, on the magnetometer module. And that is on our website, where you can go to our, let's see, I'll show you here. So if we go to the Chesapeake Tech website, chesapeaketech.com, if you go to training and webinar recordings, this has a record of all of our previous recordings, and that's where you can find this recording after we're done. We'll post it here. But if you scroll down a couple of rows, there is the original SonarWiz magnetometer video that we made, like I said, about 2 years ago. And it is super useful. It covers a lot of the basic ground of how to use the module, how to import data, how to do, most of the basic stuff. I'm going to focus today on a little bit more advanced topics, as well as the changes that have been made that aren't covered in this video here, so keep that in mind. The second thing I wanted to show you for magnetometer processing is that we have a quick start guide that will take you step by step through the program as you're processing your first few data sets. And you get to that from the support website, or the support button. Go down to knowledge base, just hover over there, click on knowledge base. And then right here at the top is the quick start guides. And we've pinned to the top here this quick start guide to magnetometer processing. So this walks you, like I said, step by step through the processing. You've got an example data set you can use, and just fire up SonarWiz, download the data set, and work your way through this quick start guide. And it covers a lot of the basic information. If there's anything that's changed, that's what this video today is all about. Okay, so I want to talk a little bit about magnetic anomalies, kind of give you some useful information before we jump into the program. So a magnetic anomaly, a magnetometer trace itself is a time series. I've got one displayed up here. And it's a time series of the magnetic field of the Earth that's been measured by a magnetometer as you tow this magnetometer through the field. When you're in an area that has no magnetic targets, no ferrous objects on the seabed, what you're recording is just the background field. And that's kind of what you see here on the left-hand side or on the right-hand side of this chart. It's never completely smooth, and I'll explain why in a few minutes. But if you do have a target, if you do have a large metal object on the seafloor or buried on the seafloor, this causes a distortion in the magnetic flux lines, and that is picked up by the magnetometer as an anomaly, as shown here. And primarily in seabed mapping, this is what we're interested in. We're looking for targets on the seabed. The other use of a magnetometer is for geologic applications, which we're not going to talk about today. So how does this distortion actually work? So this is a cartoon I got out of Peter Holt's 2016 document, and I have a reference to that at the end of this talk. So you can look this up yourself and get it. It's a really good, probably 60, 70 pages of information on magnetometer processing, primarily from the point of view of archaeology, but it's super useful. All of it applies to SonarWiz, so I think it's worth stealing a few pictures out here and showing them to you. So what we've got here is a cartoon that shows seawater up above and a seabed down below and a ferrous object here in black. And we have these magnetic flux lines in red. And we're towing our magnetometer through the magnetic flux lines. The object, because it's made of metal, is distorting the magnetic field. And where the lines pull apart, the distance between the lines represents the strength of the magnetic field. And where those lines get distorted or pulled apart, the magnetic field is slightly weaker here. And where those lines pile up on top of each other, the magnetic field is stronger. And if we do a time series of this, as we drag our magnetometer through this, when we're here, we're kind of in the background, and then we enter this low anomaly area, and the anomaly drops. The iron is pulling or distorting that field, and it causes a slight negative drop to the background. Then we get over the top of the target here where it's positive, and it goes positive, and so on. So here is a classic kind of magnetic anomaly. This is what we're measuring. And it's a distortion to the background radiation, not a complete elimination of it. Now here's another picture. This time it's a top-down view of a shipwreck here. And one of the interesting things about magnetometer data is that in the northern hemisphere, you wind up with a negative dip to the anomaly in front of a ferrous target and a positive peak behind or in the southern part of the target. So the direction that you run your run lines through this zone really makes a difference in what your anomalies are going to look like. Now, the classic line that we just showed you would be this line C. So we went from the northwest down to the southeast here. And that would be, as we're trucking down here, we go into the negative zone. So here's the low dip, then it climbs up over the peak, and we get the peak like this. This is the classic dipolar anomaly. But if we ran different lines through this area, you would see different things. If we ran line A here, we would only see the positive peak. So you get a positive peak up here. If we ran line B through the negative peak, you would only get the negative part. And if you were really unfortunate and ran this line right through the center here, line D, you would see hardly anything at all, just because of you haven't really hit any of the peaks. So the direction that you run your lines through makes a difference in what your anomalies look like. The other big thing that affects your anomalies is how far away you are from the target. So here is another example, and here we have a shipwreck or large iron object that's on the seabed. And we have 4 track lines, or 5 track lines, 0, 1, 2, 3, and 4. And the survey went from south, then looped around like this. So I've got the arrows drawn on there. So line 0 goes directly over the top of the target, and you see a nice anomaly over the top of this. We get the positive anomaly on the back side, on the south side, and on the north side, you get the negative anomaly. So we know this is in the northern hemisphere. And as we get further and further away, we're changing directions. We're going from north to south and south to north, because we're just doing a racetrack here. But the anomalies are getting smaller. The sign flips as you change direction, but as you get further and further away from the target, the anomalies get smaller and smaller. Eventually, down on line 4, you have hardly any signature at all of the target. So that's the second most important part about anomalies, is you have to be pretty close to see them at all. Another third thing you need to understand is the update rate and the sample interval. So different magnetometers have different intrinsic update rates. The older magnetometers, these proton magnetometers, could only update about once every 2 or 3 seconds. So that would be like being down here in this bottom graph where you get a sample over the target, so infrequently that you have a tough time seeing the anomaly at all. The newer style, the Overhauser and cesium magnetometers, can sample much faster. So like an Overhauser, these are both old examples, but an Overhauser is a 4 Hertz sample rate. Now you're starting to move your way up to the C or B zone, where you can start to see more of the anomaly. And the cesium, where they can go 40 Hertz, now you're up here on A, and you're seeing a really nice anomaly. So not only do you have a sample rate, but you also have to think about how fast you're towing the fish through the water. So if you're going too fast, you won't see the anomaly for small targets at all. In general, though, the faster you sample, the lower the resolution or the lower the sensitivity of the magnetometer. So you have to balance how fast you're sampling versus how much sensitivity you have. And different designs of magnetometers have different characteristics. So all of that were kind of idealized anomalies, something like what we'd see up here at the top, which is A. But in the real world, we have other effects that pile up on top of our signature. The biggest is probably a geologic background. So these are usually widespread areas in your survey, but they can change pretty dramatically from, say, the south to the north side or the east to the west side if you have a large geologic presence. So if you have rocks in your survey area that have some sort of magnetic signature, like magnetite or basalt or something like that, those can be pretty dramatic. So that would imprint on top of your anomaly. Also, you have instrument noise. The system itself can't measure a perfectly smooth line. And newer systems have lowered this noise to, down to around 1 to 2 nanotesla. But the older systems could be quite large, and sea state can matter. There's other things that can affect your instrument noise. So a real signal is really the combination of all of these things. It's your target anomaly plus a geologic signature or diurnal signature plus your instrument noise. And what you really see is something that looks like this. And I have some examples today of data that looks exactly like this. And the job of SonarWiz, or you as a user, to find these anomalies is to try to remove as much of this noise to get back to kind of a more pure anomaly as possible. There's a really important and useful concept called the minimum detectable target. And this was brought up in the Peter Holt book or pamphlet. And what this is a formula, the Hall equation, which gives us some really useful information. It relates the anomaly size that we're going to see in our magnetometer traces to the distance from the target and the mass of the target. So here's the equation up here, and it's just saying that the anomaly size in nanotesla, that's the spike that we measure, is equal to 10 times the aspect ratio times the mass of the target, W, divided by the slant range distance, which is D cubed. And here's an example down here of if we assume 5 nanotesla as the minimum a target needs to deviate from the background noise for us to detect it. So when we're looking at our time series plots, we need to see at least 5 nanotesla spike in order for us to actually recognize it as an anomaly. So we plug 5 nanotesla into here. For the aspect ratio, this would be the width to the length of the target. It's kind of hard to estimate what that would be, so you can just set this equal to 1. And for the rest of this talk, I will assume it's 1. So we'll replace this with 1. And now the equation is just deviation divided by 1 divided by 10 times the distance cubed. And if we put 5 nanotesla in there, we can make a chart like this that shows that for a given distance, how large an object, or how much mass an object needs to be for us to detect it. And I've got a couple of archaeological objects here. Like the smallest one would be like a cannonball or a round shot. That weighs about 20 pounds or 10 kilograms here. So in order to detect that, we would have to tow our magnetometer no more than about 3 meters away from the target. If we are 10 meters away, there's no way we would see it. At 10 meters, the smallest object we can see would probably be around 800 kilograms. And now we're talking about, anchors and ship anchors, maybe a big cannon if you have something like that. As you work your way up, archaeological size things, small wrecks, you can detect at about 60 meters away. They'd have to be at least 100 metric tons of iron for us to see that. And then, as you get bigger, it becomes easier and easier to detect them, obviously. But the surprising thing is that if you're looking for something small, it's actually really hard to see that with a magnetometer. You need to be very close to see that stuff. So if you're looking for unexploded ordnance or something like that, you need to run your lines very close to the seabed and very close together. And that's what this equation tells you. So one good way to use this is to determine when you're setting out or when you're getting ready to plan for a survey, if you know the size of the targets you're looking for, you can lay out your run line length and your fish depth. You can pre-calculate what is the maximum run line length that we can take, the distance between the target or the lines, and what is the altitude we have to fly at in order to detect the targets we're interested in. And so I've just shown you how to do that here. What we've got here is, here's our boat, and we've got 3 track lines. They're coming in and out of the screen. So here's run line 1, run line 2, and run line 3, and they're 15 meters apart. So the boat is now, I guess it's going away from us or towards us. And we've got a tow fish down here. That's our magnetometer. So what we want to calculate is what is the maximum distance that a target can be given this geometry. And the maximum distance would be halfway in between the 2 lines, so at point B, and it's the slant range here between the fish and point B. And so you can easily calculate this. It's just halfway between the run line distance, gives you the horizontal part of the triangle. The altitude of the fish gives you the vertical part of the triangle, and you use Pythagoras theorem to solve for the hypotenuse here. The second thing that we need to know is the sensitivity of our equipment, and that we get from looking at real data. The best way to do this is to actually take your system out into the survey area and just hang it in the water. And while it's not moving not moving at all, you get a record, a time series of kind of what the background noise is for your system. And in this example, another way you can do this is look at a part of the survey track line that's kind of flat and has no targets in it. Zoom into that area there and measure the distance of all the noise. So this signal trace here is full of noise that we cannot detect anomalies in. We can't tell the difference between the noise in the signal and the anomalies. So these numbers are actually pretty close together. So it goes from 49,375 nanotesla up to 49,376 nanotesla. So somewhere around 1 nanotesla of noise. Now we use that information with the Hall equation. So first we calculate what the max distance is, and that's just the slant range. We use this square here. So we've got a run line spacing of 100 meters, for example, max altitude of 10 meters, noise floor of 1 nanotesla. Plug all that into this equation, and we find that the smallest target that we can detect with this survey plan is 13 metric tons. So we need 13 metric tons of iron in order for us to see it. So with this survey plan at 100-meter spacing, we are not going to be able to see anything like an anchor or something like that unless we get really lucky and just happen to run right over the top of it. So it's extremely important that you compute this as you're planning out and laying out your magnetometer lines. And then later, I'll show you another way we can use this, where we can once we've done a survey and we find some targets, we can estimate what the mass of that target is based on the information we know. So let's talk about some magnetometer processing issues and solutions to problems that you might see in SonarWiz. So the basic magnetometer processing workflow is you import the data into SonarWiz, you identify anomalies and time series plots, plot the position of the targets. You may want to compute the magnetic field, the total magnetic field, or an analytic surface. And these steps 1 through 4 are really covered in that first video that I pointed out today. I'm not going to go into these in great detail here today. I will show you how to estimate the mass of targets that you find. It's really helpful if you have auxiliary information into the project also, in addition to just your magnetometer data. At a minimum, you should have nautical charts. That way you can tell where pipeline crossings are, where cable crossings are, and buoys and that sort of thing. Bathymetric data is super useful. If you have geologic information, then you can help remove that geologic, or help you in your mind see whether or not you're going to have a geologic signature in your data. Maybe you see a fault line through there or something. The known position of wrecks, pipelines, buoys, and cables is critical if you're doing this. Otherwise, you're going to be every time you run a magnetometer line, you're going to be finding stuff that you already know where it's at. Seabed material can be useful. You know, is the target you're looking for resting on soft sediments and could possibly be buried, or is it resting on bedrock where it's going to be expressed on the surface or not? And then, of course, side scan sonar mosaics. If you want to see what's down there, you need some kind of imagery. And this is super useful if you're trying to correlate between your magnetometer anomalies and your targets. So, and of course, that's the whole point of side scan and SonarWiz. So any previous magnetic surveys you've done in the area have targets moved around, etc. So these are all really useful to load into the program. So let's talk about some specific issues. So the first one are spikes and dropouts. Spikes are these short duration jumps in the measurement that are much bigger or smaller in amplitude than the background magnetic field. So in the example here, I've got this upper graph. That's what they look like. They're caused by electrical noise, intermittent communication between the magnetometer and the top side, and sometimes by really excessive motion of the fish. But these dropouts can be a real problem for analysis because all our data is concentrated up here at the top. We need a way to pull this out. So the solution in SonarWiz is new, something we're going to show you. We have improved our despiking filter, and we have a clipping gates so that you can set an upper and lower gate, and it removes all of these spikes and interpolates across the gaps where it's removed them. Or you can manually go in and delete them all. And this used to be a little bit clumsy in SonarWiz, but we've worked on really improving that workflow. So I'll show you how that goes. Another problem with magnetometer data are towfish turns. So magnetometer data is unreliable when you have turns. And here's an example of a data set that was collected by an AUV. So the AUV goes down, it basically collects a single track line the entire time for the entire mission. So all the turns are in the data set. But before you can really process this, you need to clip those out. If you don't, what happens is you get these sharp increases and decreases in the values, the amplitude values, as you're turning. And as the turn occurs, that fish can move up and down vertically in the water column relative to the magnetic flux lines, and that causes problems with your interpretation. It also can lead to more of these dropouts and spikes that we talked about previously. If you're in heavy weather, everything just gets worse. So in general, it's really hard to deal with these turns, and it's a good idea to just clip them out. And we've made that much easier to do in the new SonarWiz. We have a couple of cool tools that I'll show you for clipping that stuff out. And a survey like this, where you have probably the target is in the center somewhere, we can clip all this out in like just 5 seconds. It's really quick. And then boom, we chop all those out, and now we've got nice straight lines that we can work with. False targets or contamination of your signal. So basically, you need to think about a magnetometer as an omnidirectional sensor. It does not always point down. It points sideways and up just as well. And so you need to be careful of recording when surface ships travel close by to your survey area. If you're working in a harbor or a bay and you've got shipping traffic that's nearby, every time a ship comes by, excuse me, your magnetometer, it's going to cause a false signal. If you drop mooring line or power cables or any of those things on the seabed are going to trigger problems with your magnetometer lines. And so the most effective thing you can do is just have good logs. You need to be actively looking around while you're collecting data and making notes about what is happening on the surface. Do you see? Are you passing by targets that could be causing anomalies? Oops, I didn't. So there's not much we can do to pull this stuff out other than identify where they are. And we know that they're false targets. Okay, so effects of geology. So magnetic rocks affect the magnetic values in your survey area. And sometimes the effect is small and you can just ignore it. Sometimes the effect is really strong and it can mask your anomalies and targets. So the way you can separate these two ideas out is a magnetic or a human-made target is usually small in geographic area, concentrated, whereas most geologic formations are large relative to our survey area. If you have bathymetry, you might be able to tell that there's a fault line running through your area or a reef that's, say, basalt or something like that. Typically, though, the geologic signature is much larger than our human anomaly. So in this example on the right, I've got a line here that's going from about 49,345, and it's got a general trend all the way up here to 49,375. This is a regional or field effect. It may be due to geology, and we can clearly see where the target is. So one option would be just to ignore the fact that there is a anomaly or there is a regional shift in the data here. Or you can run a high pass filter like I've done down here at the bottom, where we run a low pass line over the top of the raw data. So the green is the raw, and we run this black line through there. And then we subtract the two from each other, which gives us just the high frequency component, just the wave number that's smaller than this large area. And that basically removes this geologic signal or this field signal. Now everything is centered around 0. So now our target is much easier to measure. So that's the way to do it in SonarWiz. And in fact, we use this high pass filter technique to remove several things, including diurnal variation. So diurnal variation occurs when the Earth is rotating. It goes, so the Earth and Sun form a system, a magnetic system, and similar to it's similar to tides, but now we're talking about the magnetosphere. And as the Earth rotates underneath that system, you get positive and negative effects on a daily diurnal basis. And this can be tens of nanotesla over the course of a day. I didn't have a really good example of this in my own library of data, so I stole a picture from Peter's book here. And he's showing there's 3 survey areas here that were collected at different times of day. And there's quite distinct shift in the background values that are due to this diurnal variation. There's a couple of ways to get this out of your data. The one that's built into SonarWiz is the first one. You filter the data using a high pass filter. It's very similar to this because everything's going to be centered at 0 when you're done. So that's one way to remove it. Another way is to manually shift each line before you load it into SonarWiz. Here they've got a tie line, I think, that thought I saw when it went right through the whole data set, but that would be a good way, is to run a tie line through all of these. And then you have a point on each track line where you can raise or lower the values until they're all the same. And then finally, probably the most sophisticated way to pull this out is if you're close to land, if you're close to shore, you can set up a second magnetometer that becomes at a fixed location, and it's your base station. Any variation in the signal of the fixed location can be subtracted off of your roving location here. So it works a lot like kinematic GPS. That's not supported in SonarWiz yet, but you could do that before you bring the data into SonarWiz. Heading bias. So another thing that we sometimes see, especially in shallow water, is especially in shallow water, you may not be able to get the fish far enough behind the boat to where it actually starts to form a system with the boat, because the boat is metal too. And so then as you go one direction, or say north to south, you get one set of background magnetic values, and then you turn around and the boat goes the opposite direction, and you get a lower or slightly higher value. And this looks like, in this example here, I've got lines alternating direction. They're going to the northwest to southeast, northwest to southeast, like this. And the northwest lines are slightly off from the southwest lines. You see the light blue color versus dark blue color here. So this is a heading bias or a leveling problem. And it is caused by the towfish being too close to the towing vessel. I've also seen this in AUVs. So if you have the magnetometer mounted in the AUV, you need to sometimes correct for this. And again, the SonarWiz hammer for this is to filter using a high pass filter, which can remove this signal. You also have the other option to manually shift each line, or to use crossing lines and calculate the difference between the different lines. In SonarWiz, we use the high pass filter to get rid of this. One final type of noise that is common in data but difficult to remove is wave noise. And again, I didn't have a great example of this, but when you have swell, the magnetometer can move vertically through the water column as you go over the waves. If that is a long swell, you might get something that looks like this here on the right-hand side. This, we could probably run a filter through this, a low pass or a high pass filter to remove the wave noise. But if you're in really choppy, unpredictable, short period chop, it's impossible to get this stuff out. So it just looks like random noise in the data set, and it basically effectively increases your minimum detectable anomaly to bigger than the wave period. So there's no easy way to get the short period chop out, and it's very difficult to remove. So it's best to avoid these. If you're in a situation where you have choppy weather, it's really a good idea just to avoid it. Okay, so let's switch to SonarWiz now, and I'll show you some of the new, I'll highlight some of these things here. The major areas where we have made changes this past year is we have fully integrated magnetometer with the user interface. So in the originally magnetometer was a small add-on module that wasn't part of the main user interface. And over the years, it's been gradually growing up. And now it is basically a full-blown peer of sidescan, sub-bottom, and bathymetry. So one of the biggest changes that we made in this release is we now have magnetometer viewing modes. So you can control the screen and what you see on the magnetometer by actually manipulating it like you would other data sets. We've enhanced the context menus, so you've now got sort and zoom to and all this kind of stuff that you would expect from a towed system in SonarWiz. We've also got, we've strengthened the links between anomalies and sonar contacts, and I'll show you that in a second. We've improved the magnetometer editor, so it's easier to clip and remove spike data. It's much more efficient, and when you're filtering data inside the editor, it's almost instantaneous now. It's much faster performance. We've also made it much easier to trim lines. So as we're starting to see more and more AUV data sets, we needed a better way to clip data out, and I think that we've improved that a lot. And just in general, the whole experience has been improved. So this is an old data set that that we keep going back to because it's got some beautiful shipwrecks in it and magnetometer data here in San Francisco Bay. And the first thing you'll notice is that the magnetometer has colored lines here. And these are controlled by the new drawing modes. So if you go to View, Drawing Mode, down here to Magnetometer Drawing Modes, you have the option to draw the residual trace. So it would look like this. That's the raw data. And you can draw the residual. So after you've filtered it, this is the filtered data. It's drawn there. And our colors are added to the color window. So you control what color palette you're going to use with, say, the raw or the residual here. And it controls this. You can pick the color palette. I picked a blue-red color palette, but you can make your own or do however you want. You can also control the size of these dots. So the plot thickness here is, I can make it really huge or small. And then if you like the old way of just drawing the navigation plot lines, you can switch back to that as well. So the second part of the user interface that's really been improved is the properties window here. Oops. Let's get that open. There we go. So this property window. So when you select a magnetometer line, you can now see all of the information we know about the CMF is the format we use for magnetometer, the common magnetometer format. And we basically added virtually every property that is recorded in the CMF file is now listed here. So you can see everything that we know about it. Altitude, the start and stop time, everything, the positioning. If you click over here to the display tab, you can control how this line is going to plot its raw data, its residual data, etc. So this is a nice new improvement. Close that. The other thing that has really changed is we flushed out all of these menus. So if you right click on a magnetometer line or the anomalies, you'll see that we've increased the number of commands that are available for these. Basically, it's now on par with the sidescan line. So you've got hide and isolate and trim and split and all of the tools that used to be available for just the towed systems like sidescan are now, we're porting them over to magnetometer. So you have all of that ability here. Same thing with the anomalies. So if you open this guy up, right click, you'll see that we have zoom to. This was a requested feature for this release. You can zoom to an anomaly or just hit the Z key. You can hide, isolate, edit, etc. When you edit an anomaly, it opens it up directly. In fact, that's a good thing for me to show right now. So before we get started, it's important to know what our minimum detectable distance is, or minimum detectable target, MDT. So let's look at this and calculate that for this particular data set. So you look for the line spacing, probably at its widest, it's about 125 meters here. So I've got a little spreadsheet here where we can enter these values in. And if you look in the handouts section, I've included this so that you can download this directly from the GoToWebinar interface. So we're going to calculate the minimum detectable target. So the first thing we know is our run line spacing is 125 meters. And now I'm going to open up a couple of these lines and just look at how noisy they are. So just double click one and open it up in, let's look at, we want to draw the raw trace and look for a nice flat area that doesn't have targets in it. So maybe like right in here, that looks like a good spot. So zoom in on this area. And we want to measure the distance from kind of the top here. This is 49,180 to maybe the bottom here, which is, 49. So maybe 160 to 120 or a little bit less. So we're talking about anomaly noise of about 20 nanotesla. So we can put that into this equation here. So if we say the minimum, maybe it's less than that. So 15 nanoteslas. Run line spacing is 125 meters. And the survey was run with it. Looks like the altitude is around 6 meters here. In the other parts of the survey, it was around 10 meters. You can kind of see how that fish altitude here, the magnetometer altitude is changing. Let's try putting in 10 meters there. And then we'll use 1 for the aspect ratio. So given these parameters, the maximum slant range that we're likely to see to a target is 63 meters. And that results in a minimum detectable target that's 380 tons. So if we look at this plot down here, 380 tons, because we're at 100, we're actually way out here. So we're 63 meters, right about here. And our maximum detectable target, or minimum detectable target, is basically ship size. We're talking about targets that are approximately the size of ships. Now, I didn't mention this, but if you have a linear target like a electrical cable or a pipeline, they tend to have a stronger magnetic signature than their weight would suggest. So this would be primarily for point targets, and I think that you'll have an easier time finding linear targets. But this gives you a rule of thumb that our magnetometer is not going to be finding cannonballs unless we're extremely lucky. So if we want to be sure that we found every target, our rule of thumb here is about 380 tons. This is the smallest thing we can see. So let's take a look at that. So I've got this line here, and it's got a target already marked down here. It is anomaly number 8. So I'm going to zoom in on this guy. And I can already see that there's side scan targets that are close by here. And so let's take a look at those. I've marked them already. Turn all our side scan contacts on. So here we have contact rec 0005, and we have anomaly 0008. There's a couple of ways we can see the connection here. So just visually, we're in the map view, we can tell that anomaly 8 is close to rec 5, and that's probably what's causing anomaly 8. So if we open up this line here, as I pan through it, right as I cross over the anomaly, we can see that connection there. So what I'm going to do is associate these two together. So you can open that by double clicking here, which is the old way of doing it. You can open this anomaly editor, or we can directly open anomaly 8. This is a new, didn't used to be able to do this. It just double click it, it opens up. And now we're going to go to cause of anomaly, and we'll identify the cause. We're going to look at contacts, and SonarWiz automatically finds the closest sonar contact, and that is rec 0005. This one is 20.6 meters away. So from our anomaly to the rec marker is 20.6 meters. So with that information, we know 20.6 meters away, and we know the altitude of the magnetometer here. So we can go back to our Hull equation and calculate how much mass is this target. So let's go back to the spreadsheet, and this time we'll go to the target mass page. It's the same equation, I just reorganized it. So we've got 20.6 meters as our horizontal distance. The fish altitude is about 9.2. The anomaly, I didn't measure how big the anomaly was. So let's open up that line again. And we're measuring, so we want to look at the residual trace. It goes from 0 to about 700. So 700 nanoteslas. Type that in. And again, we'll assume an aspect ratio of 1. And this gives us an estimate of the mass of this vessel at about 800 tons. So estimated mass is 800 metric tons. So we can put that into the notes here. So we've estimated what that is. Okay, so for the next, the other things, now we can go, we associated these two, the rec to the anomaly. So if we go to contact 5 and open that up, you'll notice that it has made an entry down here for mag anomaly is now associated with anomaly number 8. So there is a two-way connection between the anomaly and the contact. And that's all been introduced in the latest release. So the next thing I want to show you is improvements to the editor. And for that, I'm going to look at this data set here. These data have some dropouts in them here. So in this line, you can see that the main data is up here around 50,000. And we've got these drops, these spikes that drop down here to almost 0. So the quick and easy way to fix this is we know that the data is centered somewhere around in there. So we can just clip it. So we're going to say remove everything that's below 45,000 and above 55,000, and we'll just remove it. And in one click, we've now cleaned up this data set so it looks nice. So I'm not going to save it. Nope. Well, and then we'll go back and try it the other way. So now you can also manually clean this up much easier. So you can select a region and just delete everything that's in the box. So there's another way to do it. Maybe that's also a problem. So I don't know this data set well enough to know if each of these spikes is real or not. A lot of those look like real anomalies to me. But now it's much easier to go through and clean these up using the new remove. So you have the option to clip, which actually just saws it off like you were mowing the lawn, or you can pull the weeds out using this interpolate. This one's a little bit noisier. Clip that out. There we go. Sometimes have to clean it up a little bit. All right, so that looks great. And now we can do our low pass filtering, et cetera, on this data set and work our way through it. The next thing I want to show you, the new thing, is the new tools for clipping. And for that, we have this trim and split. There we go. So here we have this AUV data set, and it's got all of these turns in it. And we have a couple of ways we can quickly clean these turns out. Okay, so what we can do here is open up our single track line, and there's this new button here, which will allow us to put markers in where we want to clip the data. You can see here's this strong heading bias that's in this data, this AUV data. So if we click here, click here, click here, we're going to be able to split this line into multiple parts. So if we now right click, it'll say yes, split the line into 6 segments. And now we've taken our single line and we've broken those into individual components there. And of course, here's the one that's left over. An even faster way to do this, if you've got a nice survey area here in the center, so if our target is in here, rather than go through and find each turn and clip them out, we can just draw a box. So we'll go to post-processing here and add a rectangle. And this would be our area of interest, AOI. And I just draw a box where I want the data to be kept. So now I've got a box. If you select it and right click and then say trim the magnetometer data to feature extents, SonarWiz clips out everything that's outside of that box. And now we can work on these track lines one at a time to adjust that heading bias. We can do a low pass filter on it and clean that all out. So overall, we've added the magnetometer viewing mode. That's probably the most interesting new feature. It's now built into the interface. We've enhanced those contact menus and added a lot of the missing stuff that people have been asking for. So you can now sort contacts, you can zoom into the targets, etc. We've strengthened the length of those, or links between the anomalies and the contacts. We've improved the editor a lot. It's much easier to use now. You can trim magnetometer lines in a couple of different ways and just overall improve the performance. So I wanted to mention this, some of the figures I took out of here, and this idea of a minimum detectable target comes from this paper from Peter Holt, Marine Magnetometer Processing at 3H Consulting. And I think that this was written while he was at Plymouth University. Then I stole a bunch of pictures and stuff from Wikipedia and just recently. So if there are any questions, I have a few minutes. I can answer some questions now and be happy to. So there was what was the distance to the known target or the width of the anomaly? So the distance, so I think we're talking about, we go back to, let's go back to this guy here. So we've got our rec number 5, and our anomaly here is number 8, and we associated those two. So I use this known button here, and I identify the cause, and the distance that I used is the straight line distance from the anomaly to the target. And this is actually computed at, it's done automatically by SonarWiz. So here it gets 20.6. And the other way you could do this is just use the measurement tool and start at the anomaly and go to the target. And there I get a slightly different number. I got 19.5 meters. It's not exactly over the top. And what I do is I put those into this spreadsheet here. So the target mass, the horizontal distance from the anomaly to the target is 20 meters. The fish altitude is right here. That's how high the fish was at the moment that we took the measurement. The anomaly size I measured, actually it should be on this screen here. Duration event. Peak to peak anomaly here is 890. So that's more accurate. Let's type 890 in there. And now we're seeing that we use all the real numbers here. We get about 1,000 metric tons for the size of this vessel. Now this, if you were looking for this spreadsheet, the equation is in the presentation, but the spreadsheet should be in the handout section. I don't know if I have to actually click a button here to share it with everybody. But you should be able to download those right from the GoToWebinar meeting. So hopefully, did that answer your question about okay. If there's, I'd be happy to, so it's hard, so the way we've got this set up, we can't actually talk to each other. So you have to type your questions in there, but again, I'd be happy to answer any questions by email. It says, what if you do not have a known target to relate to? Do you assume the target is directly below the magnetometer? No, so if you don't have the known target, all you can do is assume, so the equation does assume that the target is the minimum distance. So if you have this minimum detectable target distance is going to use this, the way I showed you to calculate it, we use the slant range from the fish to the center of the lines. So if we have, here's our two track lines. There's one right here and there's one here. The distance between those two track lines is 120 meters. So the maximum a target could be would be right here in the middle. So the only other part we have to figure out is how high above the seafloor we're towing the fish. And then we use just a triangle, which was in my presentation here. This guy. So here's in this real life example is 120 meters between the two run lines. So 120 meters divided by 2 gives us B. So that's 60 meters. The altitude that we were flying at was around 6 meters, similar to this actually. So we'd have 120 times squared, 6 meters squared, take the square root of that, and that gives you the distance that you're going to use for estimating. So it's just a Pythagorean's theorem, and it's right here. And if you use the, I've just typed these equations into the spreadsheet so you can see it. So you just type in the minimum detectable anomaly, and this comes from looking at your actual traces and seeing how much noise is in a flat area that has no targets. So you just kind of measure how much noise you're seeing in there. An anomaly has to be larger than this for you to actually detect it as an anomaly. Otherwise, it's just going to look like noise. Type your run line spacing in there, type your fish altitude in there, and then the width versus height, or the width versus length, gives you an aspect ratio. And it's hard to, there is an aspect ratio here to this thing, but I'm not sure. We need to know where the magnetic field lines are to know whether it's which is width and which is height. And I just find that confusing, and I tend to set this to 1. If there's an aspect ratio that's non-1-to-1, then this is going to lower the size of the target, the maximum detectable target. Okay, thank you very much for watching, and I hope you join us in 2 weeks where we'll be talking about bathymetric analysis, the tools we built in for doing bathymetric processing and review of your data. So thank you very much.